Okay, so our approach here is that in a sample of gas, all of the molecules are in constant motion, but there is an average kinetic energy they have that depends on the temperature, not the identity of the gas. And that kinetic energy is related to the what we're calling the mean square speed, which is kind of like a statistical projection of all the speeds of all the molecules in there. So let me show you one way that we can use to get a grip, maybe a view of what molecular speeds look like. And this is a sketch of the type of apparatus you would use. Of course, it's not like this, but it's a sketch, right? So essentially what you have is you have a sample of gas that's going to be heated at a certain temperature in an oven and allowed to exit through a small opening on one side of that oven. That's over here, all right? Now, there are two discs attached to a bar that's getting rotated by a motor at a specific speed that is calibrated to be known. All right, the stream of gas particles is first kind of focused into a single stream that exits here. And the first disc is essentially a chopper. It's a disc that has a slit in it. That means that when this stream of particles gets in there, if the disc is at any position other than when the slit is in the path of the stream, the gas molecules will bounce off and not make it through. So essentially, because the slit is rotating at a certain speed, essentially it allows passage of little bursts of particles of gas, you know, every so often. But because it's all rotating at the same speed, essentially each stream is coming at the same rate, like boom, 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 right? So what's going to happen essentially is you're going to have here a stream, like a burst. Oops, sorry. It's like a burst of particles. Every time the stream passes through that slit. So what's coming on this side are little bursts, periodic bursts of these particles. Now, what's going to happen here is that the faster particles are going to be at the front of that burst and the slower ones in the back, right? So these are going to be here fast. And this one's going to be slow over here. Well, it's hard to write with a mouse, isn't it? I wish I had a touch screen where I could, like, Professor Rollback uses an iPad so you can kind of write on it. It looks so nice. Mine looks like a, you know, my 4-year-old granddaughter drew it. Anyway, so, but you get the idea, right? In other words, each burst has a set of particles. Some are faster than others. Now, each burst is going to hit this next disk, and this next disk is a detector. So it's basically going to register every time the particles hit there. But because it's rotating, the faster particles hit it first, and then they kind of like essentially smear all the way through until the slower particles hit this part over here. And of course, if you could run in slow motion, what would happen is you would have a slight delay before the next burst comes in, but the next burst hits in exactly the same spots, faster, all the way through slower. And so after several rounds, you have a dense enough smear in your detector that shows the density or the intensity of the hits at that particular spot. And also it shows the faster molecules that arrived here, right? They were the ones that hit first, and then the slower ones at the end. And what you can observe is that from faster to slower, there seems to be like a distribution, and there is more density of hits right about in the middle here, which would be kind of like the average molecules. So it's kind of like a distribution of speeds of molecules between the faster and the slower ones, with the majority of them clustered somewhere in between. Of course, you can now have a tool that maps that out or records the optical density or whatever property you can measure to kind of like correlate. First of all, given the speed of rotation, you can calculate what type of linear speed this corresponds to, what type of linear speed that corresponds to, and then based on the intensity of this, you can calculate what is the percent of molecules that are traveling at that speed, okay? So that's kind of like the way the apparatus is set up. Now, let's look at what a chart would look like. So this is a chart for nitrogen, N2. And you can see this is at 100 Kelvin. The next one is at 300. The next one is at 700 Kelvin. What do you notice about the shapes of the curves, first of all? So as it gets hotter, the curve is kind of like more spread out, more spread out. The lower temperature is actually pretty narrow. Notice when you look at what would be the, let's say, the portion of the curve that has the most molecules in it, in other words, the peak of that curve, notice what happens when I go from 100 to 300 to 700. What do you notice? The average speed, what happens to it as we increase the temperature? It increases also, right? So at 100 Kelvin, the average molecular speed is somewhere in here, let's say 250 meters per second, but at 700, it's closer to about 700 meters per second. So the greater the temperature, the more kinetic energy, and therefore the average molecule statistically has a greater speed. All right? So that's a very interesting approach. Again, this is at 100, this is at 300, this is at 700 Kelvin. All right? Now, here's the part that I think is interesting. What would happen if instead of just doing nitrogen at 3 temperatures, I take 3 different gases at the same temperature? So let's say at 300 Kelvin, what 3 different gases would be. So here is at 300 Kelvin. The first one I have here is chlorine. Chlorine has a molar mass of about 71 grams per mole. Next you have nitrogen, which we saw over there at 28. And next you have helium at about 4. In other words, these are 3 gases that differ in the sizes of their molecules. They're at the same temperature, right? What do you notice about the average speed of the molecules as the size of the molecules decreases? So the average speed increases, right? So helium, a very small atom, its average speed is much, much greater than, say, nitrogen, which is a mid-sized molecule, and much greater than chlorine, which is a bigger molecule. And again, this follows along with what we said about kinetic energy having a product of mass times velocity. So that means that if I decrease the mass, the velocity will increase at the same temperature. And that's exactly what you see here. As a matter of fact, and I'm not going to go over the derivation because I think we've had enough math for today, you can actually use thermodynamic theory to calculate that the actual, what is called the root mean square speed, all right? The root mean square speed, which is again a statistical rather than mathematical average speed of molecules, is equal to the square root of 3 RT divided by the molar mass, all right? Now, in this type of thing, if you do calculations here, be careful, because as we will see in the next chapter, the gas constant R has a component that's pressure times volume. Remember the liters atmospheres? Well, it turns out, as we will see in the next chapter, that product of liters times atmospheres is actually a measure of energy. You can convert it into units of energy. So if you take the gas constant R and express it in those terms, it has a different value. It's not the 0.08206 liters atmospheres per mole per Kelvin. It's more like 8.314 joules energy per mole per Kelvin. If you use that in there, you can actually use this to calculate all this stuff. And I mean, you can pretty much arrive at this expression. Again, I think the textbook might actually show you how it happens. I'm not sure the textbook does or not, but it's a little beyond the scope of our discussion. Suffice it to say that this is what you can get. Again, notice, if I know the molar mass of a particular gas molecule, right, I can see that it is inversely related to the speeds of those molecules at a given temperature. So in other words, the bigger the molecule, the bigger this is, the smaller this ratio becomes, therefore the slower the molecules are. So the prediction is that if I had two substances here, right, both of which can be detected by your smell. Let's say one of them is kind of some kind of a musk fragrance, the other one is a floral fragrance, okay? At some point, those vapors are going to reach your noses, right? And you're going to detect them. So let's say that you detect the floral one first. What does that mean about the speed of those molecules? They were faster, which would then suggest that they were what? Smaller or bigger? They were smaller. So this is a very, very important derivation here for us to understand. Now think about that example I just gave you. The two fragrances traveling. Now how did they get there? Well, the idea here is, this is called gas diffusion. It's essentially what it says is that because according to the kinetic molecular theory, gases are in constant motion, but that motion is random. As soon as I open the container of the fragrance, some of those molecules, by pure random motion, instead of hitting the walls of the container, are going to escape through the opening. And once they get out here, they'll start moving. They'll collide with air molecules. They'll collide with the walls in our room. And eventually, through a purely random process that looks kind of like this, they're going to end up redistributing themselves to a place where your nose receptors are going to detect those molecules and send a signal to your brain that'll make you go, ah, or maybe, ugh, right? It depends, right? So that is what's called gas diffusion. Notice that what's going to result in that is the molecules of fragrance that went out mixed with the air molecules. And so you detected the fragrance because your nose has sensors for that particular type of molecule. It doesn't smell oxygen. It doesn't smell nitrogen. Those are not gases that trigger an olfactory response, right? But that's the whole idea. Now, again, if you look at this mathematically, and if you compare now two different gases, like I compare, let's say, the vapor of a musk fragrance with the vapor of a floral fragrance, for example. And if I had a way of measuring how soon somebody got to smell them and call that, well, that's the rate at which they diffuse, I'm going to do the ratio of them, which is essentially, remember, the faster something is, the less time it took. So let's say I look at the time it took for the thing to move. So it'll be the inverse, right? What I'm going to get is that because of that equation I gave you before, the ratio of the two substances spreading out is the square root of the reciprocal ratio of their molar masses, right? So in other words, if R1 is smaller, that means this thing is bigger, and therefore R1 is going to be faster than R2, which is what we predicted before. All right. This actually is called Graham's law. And I'm going to show you an experiment now. Now, in lab, we talked about how, from one perspective, an acid and base reaction is simply the transfer of a hydrogen from the acid to the base. We saw last week, and those of you in class in lab today will see today, that that process does not require the presence of water. It does not have to be an aqueous solution. You can react ammonia and HCl gases without water, and they will react. Here is a picture, okay? So I have here on the left is ammonia, which has 17 grams per mole, and on the right I have HCl, which is 36 grams per mole. In other words, HCl molecules are bigger than ammonia molecules. When they combine, they form a product, which is ammonium chloride. You recognize that as an ionic compound, and therefore, what physical state would it be in? An ionic compound. A solid, right? So what you see there is actually like powdered form of the ammonium chloride solid. But notice, it's all clustered on this side, not in the middle of them. Why do you think that it's clustered more towards this side?
Because HU got there faster.
Very good. The ammonia got to this side faster than the HCl could get to their side because it's smaller. It travels faster, and so it got to this side just as the HCl was leaving, and therefore the reaction happened mostly on this side of the picture. And that's where you see the product being formed. So it's a very interesting observation here. Hope you like that. So remember, the bigger the molecules, the slower their average speeds are going to be. All right? So let's look at another example of this phenomenon. It's a more specific way of gases moving. It's called gas effusion. This is what happens, for example, when a helium balloon goes flat. You know, we fill up this plastic balloon with helium and it floats, right? Because helium is lighter than air, so it causes the balloon to float. And we love them for parties. But after a little while, it starts getting flat, starts kind of shrinking, starts shriveling. And the reason is that in spite of how tight the plastic fibers are, there are slight molecular openings between them. And helium atoms are very small, so they kind of like bleed through those little openings in the plastic. This is what's called gas effusion. It's the process by which a gas under a certain pressure escapes from one compartment to another through a small opening, right? So if I wanted to do an actual experiment, I would build a container with two chambers. They are sealed off from each other except for a small opening. I'm going to fill one up with the gas, and then what I'm going to do is that opening, I'm going to open it and measure the rate at which the gas moves to the empty side. In other words, the rate of effusion. Just like in Graham's law, we saw that the rate of effusions are in a ratio that is the reciprocal, the square root of the reciprocal of their ratios of their molar masses. So the bigger one will be slower, right? So we're going to use this to do another thing that we mentioned last time we can do with gases, which is using experiments to find the molar mass of a particular gas. Last time what we did, we said, if I take X grams of this gas and I measure what is the pressure in a container at a certain temperature and volume, I can calculate the molar mass of this particular gas. Well, here's another way of doing it. Let's give an example here. One of the interesting things about metals is that sometimes you can force them to make these complexes with other molecules. For example, nickel can form a complex with carbon monoxide. Now, at this point, we don't know how many units of carbon monoxide we have per atom of nickel. All right. This is similar. I think I mentioned this. The reason why when you put copper 2 ions in water, it gives you a blue color, is because the copper 2 ions are forming a complex with the water molecules that has, particular optical properties. Well, these guys might do the same. So let's say that I do an experiment where I measure the rate of effusion of this gas, and I measure the effusion of methane, a gas that I know exactly what it is, right? And I find that under the same conditions, methane effuses 3.3 times faster than my unknown compound. All right, that's my data. How do I use that to find out what is the value of X? In other words, what is the formula of this compound? Watch out. Okay, one of the things that I found sometimes is, how do you convert an expression in words into a math expression? So when I say that the rate of methane is 3.3 times faster than this compound, how do I make that into a math expression? Well, let's say this. Let's say that if my unknown is, let's see, I'm going to call it compound number 2. I'm going to say that methane, compound 1, effuses 3.3 times faster than my unknown. All right? So that's what it means. 3 times faster than the compound. That means that R1, the rate of methane, is 3.3 times the rate of the unknown compound. All right? Methane has a molar mass of approximately 16 grams per mole, right? 12 for carbon, 1 for each hydrogen, about 16. In this kind of experiment, we don't probably go into too many sig figs. It's not worth it. It doesn't have that level of precision. So let's look at this expression here. And the first thing I'm going to do is I'm going to take the square of both sides. So I'm going to take the square of this ratio, R1 over R2, and the square of, the square root of this. So that means that I knock out the square root. I make this into a full square. And now what I need to find is, what is the value of my molar mass of my unknown? Well, I'm going to move this guy over there, just squaring. So I have, R1 squared over R2 squared. But R1, we said, is 3.3 times R2. That's going to be squared times the molar mass of my known compound, which is methane. All right? Now I notice that the R2 can cancel out. And so I'm left with my molar mass is going to be 3.3 squared times the molar mass of methane, which we said is 16. And that gives me a total of 174.2. And that's the molar mass of my unknown. So if I know the composition, if I knew the actual composition, I don't at this point. I don't know what it is. But if I knew the exact composition, I could use the composition analysis and the molar mass to find out what is the formula of my compound. But all I know right now is that the compound has nickel, and then the carbons and oxygens are in the form of molecules of carbon monoxide. They're not spread out, they're actually molecules. I need to find out how many molecules of CO I have per nickel atom. So I'm going to take out this, and I'm going to say, well, nickel is about 58.7 grams per mole. Carbon monoxide is 12 plus 16, is about 28 grams per mole. But I have X units of that. All right? And that has to add up to 174.2, which means I can subtract 58.7, divide that by 28, and I get that X is approximately 4. So that means that the formula of my unknown compound was nickel parenthesis carbon monoxide, 4 units of carbon monoxide for every atom of nickel. So there you have it. We now have two different ways of using the properties of gases to calculate the molar mass of an unknown. The first method last week was using the ideal gas equation. The second method is using Graham's law. If I have a method for kind of like comparing the rate of effusion of an unknown gas versus a known gas. All right? Okay, so the kinetic molecular theory of gases, and emphasize again, it's a theory, right? Which means that, yes, it's been tested, it's been proven, but it's always open to there being, contrary results, results that don't match it. But it's good in the sense that it explains the behavior of gases, why gases are ideal. It allows us to draw comparisons. If we know the identity of two gases, we can predict what the rate of effusion of each is going to be, or the rate of diffusion, or vice versa. If we know the rate of effusion or diffusion, we can back calculate what is the molar mass of an unknown. So very useful, very powerful tool. But of course, like we said, it is a theory. And there are conditions under which it doesn't work. So I'm going to talk briefly here for a couple minutes about some of the deviations from ideal behavior of gases.